So lab, I'm still looking for a possible way to sneak in another lab. Maybe take lecture time and do a lab, so we'll see. My other thing, and we'll get to it in part 6, the last part for chapter 8, but boy, wouldn't it be awesome if we could go to a water treatment plant or so we'll see. I don't know. Can't figure out how to do that. But I looked online, and Keokuk, they have tours.
Yes. Should be pretty easy to go through.
Yeah. So I'm kind of, I don't know, think about that, because I think that would be,
That's cool, let's go.
yeah, right? So let me think about it. But in the meantime, what we left off with was you guys knocked out the pHs for these 4 liquids, or given that hydrogen ion concentration. So
you can only do that with the hydrogen ion, you can't do that with
OH. No, you can do it with OH too. OH
it's the
minus.
same way?
It's the same way. Yep. So what your question was is if, for instance, whatever pH you had for this, and we're going to talk about the relationship between the H plus and the OH minus, but if that was the OH minus concentration, to get the POH, all you would do would be to take the negative log of 4.5 times 10 to the negative 5th. And that would be your POH, if that was the hydroxide ion concentration. Which leads me into a good point. It can't be, and I'll tell you why. If you have some water or any aqueous solution, if you were to go and to knock out, remember brackets means molar concentration, if you were to go and knock out the molar concentration of the H plus and the molar concentration of the OH minus, multiply them together, it's supposed to equal, at 25 degrees Celsius, 1 times 10 to the minus 14. It's a constant. So if that's the case, if one goes up, the other needs to go down. Okay, and if one goes down, the other will go up. So it's multiplied together to equal that same number.
What did you say brackets mean?
Brackets means molarity. Brackets means molarity, yeah. So Kw, that 1 times 10 to the negative 14th, again, it is temperature dependent. That Kw is what we call the ion product constant for water. The ion product constant. And if you dabble further into chemistry, you're going to see that this constant is actually related to the fact that an equilibrium is involved, basically. So let's see how that would work. Oh, wait, I'm going to see it in a minute. Before I go there, I want to talk about the 3 possibilities: neutral, acidic, and basic. And I think I touched on it the other day. Remember when I drew this, and you're going to see it here in a minute, if this is my pH scale, it goes from about 0 or 1 to 14, and in the middle is pH of 7. So these are my pHs. And if it's neutral, I'll put an N for neutral, then your H pluses are equal to your OH minuses. That's it. Oh, sorry, pH 7. So what do you think this is? If your H pluses are greater than your OH minuses, is it acidic or basic?
Oh, wait, it is more?
Mm-hmm. It's acidic, yep. And so will your pH be greater than or less than 7?
Less than.
pH is less than 7, yep. Very good. So the third scenario is this one, where your H plus is less than your OH minus, and you must have a blank solution. Basic solution, yep, and your pH will be greater than 7. Yep. 3 possibilities. Okay, so now back to this up here. So for any solution of water, aqueous solution, your H plus, your molar concentration, and your OH minus molar concentration multiplied together is going to give you 1 times 10 to the negative 14. Well, for A, we know this. We know the H plus. is 1 times 10 to the negative fifth. How can we get to the OH minus?
You divide 1 times 10 to the negative 14. So
Yep.
1 times 10 to the negative 14.
All we got to do is take 1 times 10 to the negative 14th and divide it by 1 times 10 to the negative fifth. Now I think I'll start going around the room here because I like that. So, Autumn, what do you got?
1 times 10 to the negative 9.
1 times 10 to the negative 9. Cool.
So is that always the rule when you're doing dividing?
As long as this number is the same, in this case, this is called the coefficients, as long as it's 1 and 1, you can go ahead and just subtract the exponents to get the answer. Yep. Any questions about that? So 1 times 10 to the negative 9th. Okay, Billy, what about the next one? Sorry, that's not equal to, I should have, oops, is equal to the OH minus, final answer. Okay, how can we get the OH minus from that H plus? And what do you get? Mm-hmm. Yep. Is your OH minus. Perfect. You got it. What about the next one, Taylor? How can we get H plus? And what do you get? Yep. I guess I should, I'm going to put a big M there. Of course, that stands for molar. Okay, last one. Glenna? How could you get the H plus molar concentration? I hope that'll work on a... Okay.
It's negative and negative.
Well, since the one's in the numerator, one's in the denominator, basically you're taking the negative 4 and you're subtracting a negative 4 from a negative 14. 10.
10.
Yep. Negative 10th. Yep. Very good. Okay, cool. So this is the pH scale we've been talking about. You know, acidic, basic. So what do you guys think if I were to add, so this is the molar concentration of the hydrogen ion. What if I were to put the molar concentration of the hydroxide ion? Hey, Natalie.
Hi.
So let's just pick this first one. Autumn, what do you think? What's the molar concentration of the hydroxide ion if the molar concentration of hydrogen ion is 1 times 10 to the minus 1?
1 times 10 to the negative 15.
I'm getting that. Yep. You see where she got that? So 1 times 10 to the negative 13th. Perfect. Because, how'd you do that?
It's the same thing that we were just doing, right?
Yep, it's the same thing we were just doing.
So when it got over to 14, it'd be 0 1 times 10.
Yeah, yeah. Yep. You got it.
You said that.
Yeah. You got it. And then this, do you want the slabs closed too?
Oh, sure, that's fine.
All right. pH scale. I love it. Okay, so Natalie, you're just in time to be picked on. Okay. So rank these, and which of these do you think is least acidic? So rank them in order of increasing acidity. So which one is the least acidic?
Water.
Water. So let's see, I'm going to put it over here. Least acidic. Billy, what do you think is the next one? Increasing acidity. What's that, milk? Taylor? Oh, don't look, that's no fun.
Coke.
What's that?
Coca-Cola.
Coke, okay. Cola. Then? Increasing acidity. So we did the water, the milk, lemon juice. And you don't really have a choice there. The next one would be tomato juice. Let's see how we did. So these are some common things. Let's see. Milk is, so water, we're doing pretty good. Water, milk, tomato juice would have gone next. But we did cola and lemon juice. Not bad. Just
Good water.
yeah, it should be on your. It's not, oh, it's not on your sheet? Oh, sorry. So the real answer was simply to take tomato juice and to move it over after milk. So it's funny how we consume more things that are acidic and enjoy them than things that are basic. I think one of the characteristics of something that's basic was it's bitter, so that makes sense.
Why is milk acidic?
Why is milk acidic? It's not very acidic.
I always thought it was.
Milk of magnesia is basic. Milk is acidic. I don't know. I'd have to, well, one of the things in milk, you know, if you're lactose intolerant, it's a milk thing. And I know that there's lactic acid, so I imagine there's lactic acid in milk. So, it's interesting. Okay, so where were we? Leave off. Oh, I think we're a few Autumn. So, again, I mentioned this when I introduced the pH scale, that anytime you move one pH unit, it's not just one. In terms of the hydrogen ion or the hydroxide ion concentration, you're looking at a power of 10. So, in other words, then, you're supposed to, two questions, which is more acidic, and then how much times more acidic is it? So, Autumn, what do you think? Which is more acidic, rainwater or lake water?
Lake water.
Lake water is more acidic, and how many times more acidic is it?
1 times 10 to the 30. 1 power of 10.
1 power of 10. I'm liking it. So it's just 10 times more acidic. And the way she got that was there was a, if you take 5 minus 1 or whatever, 5 minus 1. If you take 5 minus 4, you get a unit of 1. And each unit of 1 is a factor of 10. Okay, so Natalie. Which is more acidic? Ocean water with a pH of 8.3 or tap water with a pH of 5.3?
Ocean water.
More acidic? So the lower the pH, the more acidic. Yep, so tap water is more acidic. Yep, more acidic. And then I think I'll break this up, unlike what I did for Autumn. So, Billy, how many units of pH units are there between 8 and 3? 8 and 5. Goodness, 8.3 and 5.3. How many pH units are there?
3.
There are 3 units. All right. So 3 pH units. So back to you, Taylor. 3 pH units. Each pH unit is a power of 10. So how many powers of 10 we got? And what is that number? So in other words, more acidic. In other words, the The tap water at this pH is 1,000 times more acidic than the ocean water at that pH. See how that goes? And the ones I've chosen are only like nice little fresh units, so you don't have to try to kind of chop up between them. You're looking like you don't believe in Philly.
No, I don't.
It's just trying to tell you that pH is a big hairy deal. So let's break up the next one. Which one's more acidic, Glenna? Tomato juice at pH 4.5 or milk at pH 6.5? Tomato juice is more acidic. And then breaking it up, so this is more acidic. Breaking it up, how many pH units are there between these two, Autumn? There are 2 units. So on to you, Natalie. If there are 2 powers of 10, how many times more acidic is tomato juice than milk? Your hint's right here. 10 raised to the second power is 10 times 10. Ten times 10. So 10 squared is 10 times 10. Calculator. You don't have a calculator. Ah. All right.
Can you do accounting stuff on that?
I'm just thinking, man, what's that?
Can you do accounting stuff on that?
Can I do calculus?
Accounting.
Accounting stuff? No. Its own science. It doesn't do business or anything like that.
Curious.
I know.
Sorry. Someone's got to do it. I appreciate you doing it because I don't. So 100 times. So in this case, tomato juice is 100 times more acidic than milk. Okay. So on to part 6, which is the last part, I promise. Promise. I'd love to get through this one. But this is the part that I got thinking about. Oh, man, that'd be fun. Has anybody in here been to water treatment plant? You have?
There's a bunch of community service.
Community service?
Yeah.
Oh,
They test the water every day. Under the can.
Okay.
They test
okay.
the water every day.
Every half hour? Now, was that for the coast? Was it the treatment plant or was it the municipal water?
I think it's a treatment plant. They just have it on.
Because one like deals with sewage and one deals with like the water.
Oh,
we
it's
drink.
not the sewage, it's the water.
Water we drink. Okay, the water we drink.
It's interesting.
It's interesting. What's that?
It was interesting.
I bet. Okay.
They had me mop the floor with bleach. Water treatment, you know.
Yeah.
You see
Right.
questionable.
To wash the floors with bleach?
Yeah.
Hmm. Oh.
You gotta be so careful on water treatment.
Right, because there's these big vats of water on both sides and I'm sitting down on.
Oh, I see your point. Yeah. Well, when we talk about how they purify the water, they use hypochlorite, and so they do chlorinate
Yeah.
our water. But there are alternatives to that. But all right. So the word is dissolve, and then the other word is acidic. So the other day, you guys grabbed some samples and brought them here and ran some tests on them. One of the tests was the chloride ion, and one of the tests was the pH. And if you were just to grab rainwater, I don't know if any of you guys drink rainwater, but rainwater in general is acidic. Have you heard of acid rain? Rainwater is acidic. Acid rain. That's kind of what we got going on here. And how does rainwater get acidic? And it's because carbon dioxide increasing, decreasing, or staying the same in our atmosphere? It is increasing, yeah, increasing. It crossed the 400 parts per billion threshold a few years ago, and now I looked last night, I think we're at 417 or something. But anyway, so carbon dioxide is increasing, and carbon dioxide reacts with water in the atmosphere to form H2CO3. H2CO3. And H2CO3 is just itching to be an acid. We said something's an acid if it kicks off or donates an H+. It wants to. It totally wants to. Carbonic. It even has the word acid in it. So this is just one of the things that naturally happens. So carbonic acid then can dissociate. The word dissociate means to break up, and can kick off a hydrogen, and it can make the precipitation, the rain, as acidic as 5.3. Now again, I hope you kind of have a sense for how far away 5.3 pH is from a pH of 7. You know, it's a fair bit. So here's what it looks like. Here is your carbonic acid, and here it is kicking off an H+. So H2CO3, and you can put the AQ if you want. I usually get kind of lazy. And it has an arrow, goes to form H+ plus HCO3 minus. So this is what makes it acidic, okay? And just so chemistry colleagues don't give me too hard of a time, I'm going to take this arrow and I'm going to add to it. Actually, it goes both ways. So it goes from left to right, and it also goes from right back to left again. So I'm going to draw another little arrow underneath it. It's in what we say equilibrium. It's not a one-way arrow there. It's a weak acid. And then I'm going to add one more thing. So this was carbonic acid. This guy over here is bicarbonate. Bicarbonate. So sodium bicarbonate. Oh, you've heard of sodium bicarbonate before? Sodium bicarbonate. I get my baking soda. I think it's baking soda. Sodium bicarbonate. All right. So that was rainwater. Well, what rainwater tends to be acidic. And of course, if you think of the water cycle, the rainwater is a big source for water in our oceans. So our oceans are generally, our oceans are not acidic, they are generally basic. And these are the things that make them basic. So I don't know if you remember, but something is a base, and I'm going to show it being a base like this with the letter B, and I'm going to go ahead and show a negative sign there because a lot of bases, it works out well if they're negative. What a base does, and I'll put BASE here, what a base does is it accepts or picks up an H+. That is a base. So can you see where this is carbonate? Oh, sorry, you guys need to sign anything. Carbonate is CO3 2 minus. Bicarbonate is HCO3 minus. And carbonic acid was that H2CO3. What I started to say is, can you see where this guy right here, for instance, it wants to pick up, it'll even pick up 2 hydrogens. And when it does that, it is acting as a base. HCO3 minus 1 is what it's going to form. I could go ahead and add an H plus to the middle guy, and then what it would form would be H2CO3. Now again, I'm doing one-way arrows, which is probably not right, but I think it works for this discussion. Probably 2 arrows, equilibrium. So, but that's how in the oceans, the presence of these dissolved in the oceans then accept a proton and make the oceans basic, which I didn't know.
How
Okay.
does it make it basic if it ends up being acid?
What's that?
How does it make it basic if it ends up being acid?
Yeah, this is an acid over here, which would, you're right, this would donate protons. Your thinking is right, that this would actually break up and do that. But
It just keeps cycling.
but what?
Does it just keep cycling?
Yeah, it keeps cycling. And I think one way to think of it is that it's not, this guy won't make it basic, but these two guys will make it basic. So, the shells of little organisms in the oceans, crustaceans in the oceans, their shells are made of calcium carbonate. And of course, this is carbonate. So calcium carbonate is what the shells of the ocean are. So my hint down here is show, well, I just did it for you. It says show how carbonate, the first two, and bicarbonate can make the water basic. All right. So, ocean is generally basic. I don't think it's very basic, but now it makes me wonder. But we have this acidification process going on where carbon dioxide is dissolving. Carbon dioxide is increasing in the atmosphere, and one of the things we know about a gas is that if you increase that gas, and that gas is hanging out over water, like the atmosphere is hanging out over the oceans, just inherently you're going to get more of that gas dissolved. It's called Henry's law. Okay, so you would just get more of that gas dissolved. So more carbon dioxide dissolves in the oceans, and it makes the oceans more acidic. And I feel like we've come full circle. I don't know. It generally makes the oceans more acidic because of the formation of carbonic acid. That's kind of what your point was. So let's watch this video and then we'll take a look at the figure. pH for everything. As it turns out, you see the range there for normal aquatic life, a little bit acidic to kind of basic. And then you can see what happens from right to left as it becomes more acidic. Fish disappear. Aquatic life in general disappears, and then the lakes become dead. And I got these facts from your textbook. So, for instance, in other countries that have been affected by carbon dioxide acidifying their lakes, the problem with lakes is that they are isolated versus an ocean. So about 1/5 of the lakes in Norway and Sweden are zilch, uninhabitable for fish. Ontario, Canada, the pH of their lakes is pushing 5. So, and in the United States, let's see. See, in the United States, acid rain is most concentrated in our northeast. So northeast. Why do you think it would be the northeast? Yes and yes. Yep. Northeast. Goodness. Ugh. Yeah. And so to me, kind of that's why Canada, Ontario got hit hard too. Another reason, we just talked about this in my meteorology class, is what direction does the wind blow here? From where to where? In general. Other way. From the west to east, yeah. If we kind of want to look at our storm systems, we'll look in the west and kind of watch them march across the United States. So kind of with that in mind, not only over here are we highly populated in the northeast, we have industry, but it just kind of, if we had anything downwind, it's all going to kind of accumulate. What's that?
That came under the thing that you wrote up there.
Oh, I did. Oh my gosh, thank you. Okay, so in this area, I thought this was interesting. I read it in your textbook. Maybe you did too, that we have our limestone actually is calcium carbonate. Go figure. So one of the things that carbonate can do, calcium carbonate, CO3 2- is a proton acceptor. So what your carbonate can do is to make things actually, they can fight acid. They can fight acid in our lakes and stuff. Oh, yeah. There's a 2 here. Sorry. I was going to ask you guys, do you see where if I had to put a 2 here? You guys have to finish this. So on the product side, we have the Ca2 plus, and then we have 2 HCO3 minus. To have the same number of, as we check the element on either side of the reaction arrow. So I think I'm going to skip this for now. No, let's not. We can do this. Okay. Who do we leave off with? We'll just, I think it might be Taylor. We'll pick on you first. Okay, Taylor. So we're going to write an equation for the bicarbonate reacting with carbon dioxide. Oh, wait. Write a balanced chemical equation. No, all I want to do is show bicarbonate accepting a proton. So, what's the formula for bicarbonate? Yep, HCO3, and is there a charge? Minus, just -1. Cool. I'm going to put H plus here. So, Glenna, what do I get if I take HCO3 minus and add an H plus?
We get the carbonic acid.
Yep, and what's the formula?
H2CO.
Yep, very good. Perfect. So my point is that the presence of this, and I'm going to go ahead and put the word limestone under it. Limestone helps to actually take hydrogen ion out of our water, which means it helps fight acidification. And I kind of answered my own question here. So in this case, the bicarbonate is acting as an acid. So I'll circle the word acid. Very good. So we're switching gears here now. We're actually gearing up towards a different topic. And the topic is going to be treating water so we can drink it, municipal water treatment plants. And there we're going to be dealing with these two chemicals, aluminum sulfate and calcium hydroxide. So the first thing I'd like to do, we'll go around the room, is I want to write, I call them component ions. So for instance, Autumn, sulfate, what's the formula for the sulfate ion? Do you remember? It is SO4. And do you remember what the charge is? It's a negative. Minus, is it -1, 2, or 3? -2. Yep, that's the sulfate ion. Very good. We've been talking about hydroxide, so what do you think, Nat? Hydroxide, what is it? What does it look like? It's what water breaks into, H2O breaks down to H plus, what else? So, H2O, H plus, and then what else do you have to have? What else do you think might be? If you take away one of these hydrogens, what else do you have?
Oxygen.
Oxygen and, because you only took away one hydrogen.
Hydrogen.
Yep. Do you remember charge? Plus, minus?
Plus, -1.
Yep. There you go, hydroxide. OH minus or -1. Okay, calcium, Billy. I'd use the periodic table to find where it is and get a sense for what charge it'll be. Yep. Calcium +2. And Taylor, how about aluminum? Very good. Okay, and then it goes like this. What are the compounds that can be formed? So, for instance, Glenna, and I love ionic compounds because I'm going to put an A here for anion, I put a C here for cation. Basically, you grab a cation, you grab an anion, and you run with it. I wondered why my computer's getting dim. It's because it's telling me it's going to run out of juice. So what if we grab calcium and grab sulfate, Glenna? What would the form? What's that? Perfect. Yep, the 2's would cancel out because they're both, calcium's a +2, sulfate's a -2, so what would the formula be? Yep, Ca, yep, and we usually go cation first, so it'd be CaSO4, perfect. Yep, you got it. So Ca2+, I'll put comma, SO4, 2-. You combine those two together and you're going with CaSO4. I agree. So, Autumn, what if we take the Ca+2 ion and let's combine it with the hydroxide? What does that look like? Okay, so we're gonna, when we write the formulas over here, we're not gonna include the charges. We need, I think, 1 Ca, and how many OHs do we need? Yep, 2 OHs, very good. So if we need 2 OHs, we're gonna put that in parentheses. CaOH2, cool. Well, let's switch it up and let's grab aluminum. So over to you, Nat. I have aluminum +3, and what do I need to, see if I combine it with the sulfate. I guess what would happen if I combine it with the hydroxide? What would my formula be? So how many aluminums do I need? 1. 1 aluminum, and how many hydroxides do I need? I need 3 hydroxides. Yep. I call it crisscrossing. And that might be it, because the other one, aluminum sulfate, I've got up here. I should have had that one. Anyway. Okay, so the last one, hypochlorite, ClO-, it's used as disinfectant. Write the chemical formulas for hypochlorite, for sodium hypochlorite and calcium hypochlorite. So, first off, help me out, Billy. Na, what sort of cation does it form? Na and what charge? +1, yep. So what if I combine Na +1 and HClO -1? Taylor, what would the formula be? Yep, NaHClO, perfect. Okay, switching it up. Calcium, what charge is calcium, Glenna? Perfect, calcium's +2. So then Autumn, if I'm going to combine it with hypochlorite, ClO-, what is the formula going to look like?
Ca
Yep. Ca parentheses ClO2. Perfect. Very good. Well, we didn't get through it, but we're close. It's the chapter that never ends. So we'll finish up, I promise. Now remember, you have a test that opened yesterday, and you have through Monday to take it. And it does include this stuff, so, but we're almost done.